There's Esther, Malia, and Lee. This is for you. Solving optimization problems. First, you got to decide, or you got to know what it means to optimize something. You ever heard that word? Any idea how you've heard that word? How? Very good. What? There you go. There you go. Make the most of it. What optimization problems are in calculus? She said make the most of something. What optimization means in math is maximize or minimize. Oh my goodness. Find extrema. Okay. Now, I know, who knew? I want you to look on your device at those 5 steps. It will take you a little bit of time to write them down, and I think that's time wasted right now. Let's read through those. And then what we're going to do is we're just going to jump in with both feet and work problems. The general approach to solving optimization problems. Number 1, determine the quantity that is to be maximized or minimized. Duh. Number 2, draw a picture. Define a variable or use some formula to identify the quantities that are not valued. That means that don't have, like it doesn't say that the surface area is 12 or whatever. Number 3, write a primary equation that represents the quantity that is to be optimized. This equation may or may not contain more than one variable. Number 4, if the primary equation contains more than one variable, a secondary equation will need to be written that involves the same variables so that one variable can be isolated to show a relationship between the variables. You may look at that and go, I don't have a clue what that means. Yeah. Number 5, substitute the result of the secondary equation into the primary equation, yada, 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 yada. Those really don't mean anything until you get into a problem. So let's get into a problem. Look at example 1. I'll walk through the steps with you as we do a real problem. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? What is the maximum volume? Okay, look at your device. It says number 1, determine the quantity that is to be maximized or minimized. What are we trying to we are trying to maximize volume. So we want to maximize the volume. Got it. Step 2, draw a picture, define a variable, or use some formula to identify the quantities not valued. We can draw a picture. We have got an open box with a square base. So I want you to, as best you can, I don't know why I did that because I can cheat. You're so funny. You're so funny. I don't even want it right there. I want it right there. There we go. Now the rest of it won't look so good, but we're just going to pretend. That's not terrible. Square base. If the base is square, I know that the dimensions of the base are the same. Does it say we have a cube? No, it says we have a box with a square base, so I cannot assume that the height is the same as the dimensions of the base. Call it Y. I got a picture. Now it says, number 3, write a primary equation that represents the quantity to be optimized. I want to optimize the volume. Can I write an equation for volume? How? That's it. So I want you to write V equals x squared y. See, we've gone through 3 steps box already? Now notice it said on the end of step 3, it said the equation may or may not contain more than one variable. This one contains more than one variable. When it does, you have to use step 4, which is write a secondary equation. Why, you may ask? Because we cannot take a derivative, which is how you maximize or minimize, right? With two different variables. We can't do it that way. So what we got to do is boil that primary function right there. We got to boil that down to one variable. Oh, but look what else we know. We know the surface area is 108 square inches. I want you to look at the picture. Can we write a formula, an equation for surface area? Remember, it's an open box. Surface area is just the area of all the sides added together. What's the area of the base? What's the area of the front? And what's the area then of all 4 of the sides? So total will be 2x. No, not 2. I got an open box. So what's the surface area? So x squared plus 4xy. And I know what that equals. It's 108. That's my secondary equation. That's okay. Yes, it does. But if you'll notice on that secondary equation, I have like an answer to it. I know that the surface area is 108. Now, I want you to look at, we're on number 5. We're on step 5. Step 5 says substitute the results of the secondary equation into the primary equation if necessary. Stop there. I need this equation to be boiled down to one variable. So I could take this equation, I could make it say y equals, and then I could substitute. And then that volume equation would just have x's in it. How can we take this equation right here and make it say y equals? Subtract x squared and then do what? So y equals 108 minus x squared divided by 4x. You can, if you want, and I'm going to, simplify that. Remember, when you have a single term in the denominator and a numerator that's added or subtracted, you can split it into separate fractions. 108 divided by 4, that works out nice. What's 108 divided by 4? 27. So this is 27 over x minus x over 4. I'm going to take that and I'm going to substitute it right here because that's what y equals. You with me so far? So the equation I'm going to have, and I wrote so darn big that I'm going to have to scroll a bunch. V equals x squared times 27 over x minus x over 4. Go ahead. We're going to have to maximize. And remember, to find extrema, I've got to figure out what my critical numbers are. And my critical numbers come from doing what? Where the derivative is 0 undefined. So I'm going to take the derivative of this thing. And so to make me a little happier taking the derivative, I'm going to go ahead and distribute that x squared. Because otherwise I got to do product rule. Yeah, oof. So let's not do that. What's that going to give me? 27x you buy that? I got people who are either sad, sick, or don't want to be here. All the above. Didn't plan to say it so I could hear it, did you? Look at the last part of number 5. It says, then differentiate the primary equation to find the maximum or minimum. All right, here we go. What is V prime? Keep going. Will that ever be undefined? Nope. Can it ever equal 0? I bet you imagine it can. Well, we got to figure that out. Yeah, I know. My words come out like mush sometimes, but oh well. How do I solve that equation? Yeah. Multiply both sides by 4/3. X squared equals 36. X equals plus or minus 6. Now, are you okay to that point? Now, is -6 even a viable answer? No. So number 1, we got to throw that out. Number 2, you have got to, and you're going to be like, why do I have to? Because you don't whine about it and you do it. You have to show that 6 is actually a maximum, which means you got to put it on a sign chart. Yeah, don't groan. I don't want to hear it. Yeah, quit. Quit. Why did I cut my number line off at 0? I cannot have a negative length, so I'm going to cut it there. I'm going to check 2 and I'm going to check 10. I could have checked 1 and 11. It doesn't matter. If x is 2, 2 squared is 4, 3/4 of 4. 27 minus 3, positive. Oh, well, I just know 10 makes it negative. No, you snap, you try it anyway. If x is 10, I know you people. I've known some of you for too long. No, I'm kidding. I love you both. I love you both. If x is 10, 10 squared is 100 times 3/4, 75. 27 minus 75 is negative. Is x equals 6 a maximum? Yes. Now let's go back and answer the question. And you have to write sentences. Why do we have to shut up? Because you do. What are you doing? Don't answer it. I saw what you did. Don't answer. Don't do it anymore. It is rhetorical. I saw what you did. What dimensions will produce a box with a max volume? We got x equals 6. So what dimensions will produce a max volume? 6 by 6 by what? Plug it back in where? Look right here. I'm going to plug it back into that surface area. What's 20? Okay, 27 over 6 minus 6 over 4. Oh, stop it. 27 over 6 minus 6 over 4. Will that simplify? Six over 2, which is 3. What dimensions will produce a box with max volume? A box with dimensions 6 inches by 6 inches by 3 inches. That's supposed to be volume. The second question was, what is the max volume? Say again. Is it really? Is it the same as the surface area? 108 what? Cubic inches. And that, ladies and gentlemen, is how you do optimization problems. Okay. A box is to be built from a rectangular piece of cardboard that is 25 centimeters wide and 40 centimeters long by cutting out a square from each corner and bending up the sides. Find the size of the corner square, which will produce a container that will hold the most amount of soup. If you have ever bought, well, listen, if you buy chicken broth, you can buy chicken broth in a waxed cardboard box. You can even buy wine in boxes now. It's just unnatural. Is that what you said? Just unnatural. Okay. We've got a rectangular piece of cardboard that's 25 centimeters wide and it's 40 centimeters long. You have to draw pictures. We are doing step, oh, we didn't maximize. What are we trying to maximize? No. What are we trying to maximize? I would have ended up doing it next, but what are we trying to maximize? The most amount of soup volume. We're going to cut a corner out of each, cut a square out of each corner. And then we're going to bend up the sides. So we're going to end up with this box. It's probably going to have a top, but let's just assume they're putting some separate kind of lid on it. That's what we're going to have to assume. All right. What's that length? Oh, first of all, I got to know what that is. Yeah, I don't know how big that corner square is going to be. Yeah. So what's this length right here? No, that length's not 40. Yeah. This is 40, and I got 2 of them. Okay. And this length is, what's the height of the box? Now I got to maximize volume. How do I find volume? Length times width times height, right? There's my equation. 25. Yep, got me on that one. Now, here's my question. Do we need a secondary equation? We don't. Number one, we don't have any information to give us a secondary equation. Number two, how many variables do we see sitting here? Just one, just the x. So we're going to take the derivative. But if we're going to take the derivative, if I can leave it like that, I got to do the product rule, and that's going to be a bear. So we're going to multiply it out. Is that what you started to do, product rule? Yeah, we don't want to do product rule in this one. Here's what I would do. I would multiply that x by that first, and then I would FOIL. Is that 1,000? Yeah, I'm just going to wait for you guys here. I've got 4x cubed. Tell me if I screw it up. Minus 130x squared plus 1,000x. Is that all right? Hold up. No, sir. That's a rewrite. That's just, yeah, that's just simplifying combining like terms. V prime. What's V prime? Keep going. Well, I don't know about you, but I don't want to try to factor that. I'm sorry? Will that help us to factor it? I don't know. I would tell you that this, I would certainly assume this would be on a calculator part. If you divided them all by 4, would we get something that we could factor? 65. Is that 65? X plus 2. Ugh. Will it? Will it factor? It'll factor. Okay, Mackenzie says it'll factor. Will that give us 3x? Oh, go together. Okay, I'm with you. 50. By golly, that does work. All right. That's good. That's good. So be. Your mortal brain isn't capable. What's x? 50/3 or 5? Now, obviously, if you had a calculator, you could put that on your y equals graph it, and what would you look for? Zeros. You'd be looking for your zeros, which are going to give you these. Now, are those both, we haven't done a sign chart yet, but are those both even legit possibilities? 5? Could these chunks be 5? Yeah, they could. Could those chunks be 50/3? 50, what's 50/3? What's 50 divided by 3? 50/3. What's that, 116 and something? 16 and something? Is that a viable answer? Why? Yeah. So 50/3 is not even a viable answer. Yes, you do have to do a sign chart. Don't mess with me, sakes. Okay, we know that's not even viable. 0. Why did I stop it at 0? I cannot have a negative box. All right, 5. I'll check 1 and 6. If x is 1, positive or negative? If x is 1, negative. If x is 1, and a positive times a negative times a negative. If x is 6, 3x minus 5, 3x minus 50, negative. So I've got a positive times a negative times a positive. Does x equal 5 give me a maximum? Yes. So, go ahead. Yep. How could it not be a maximum? You are just verifying your work. That's what you're doing. You are just verifying your work. We were finishing this problem up. What should, oh wait. Okay, I'm trying to get my mind back. Let's see, we got 5. Did we verify? Okay, so we know that x equal 5 achieves a maximum. So let's look at what the question was. Find the size of the corner square which will produce a container that will hold the most amount of soup. So what's our sentence going to say? A, a square of size of 5 by 5, is it centimeters, inches? Centimeters. A 5 by 5 centimeter square will produce a container that holds the maximum amount of soup. Make sure you write the sentence. Well, I repeat the sentence. A 5 centimeter by 5 centimeter square will produce a container that holds the most amount of soup. Here we go. Okay, a rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the paper of the page be so that the least amount of paper is used? Draw a page. Now we've got print that's in a rectangular shape inside the page. That's pretty good. It's a little off, but we're going to pretend it's good. The margins at the top and bottom of the page are 1.5 inches. So I'm going to put right here is 1.5 inches, and right here is 1.5 inches. I don't know why I put, yeah. The margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? What am I trying to optimize? Maximize or minimize? I'm trying to minimize the amount of paper, right? Which in this case is going to be area. Now, if you'll notice, I've got 2 areas. I've got the area of the print, and then I've got the area of the entire page. Here's the way I do it. I'm going to let this be X, and I'm going to let this be Y. Now, I need you to understand, your author may do it differently. It's not a problem. You're still going to get the same answers. What's this length right here? X plus 2, right. Yep. Mm-hmm. You okay so far? Now, I want to minimize the total amount of paper. So I want to minimize the area of the whole sheet of paper. We need to write an equation for the area of the whole sheet of paper. The whole sheet. Two variables. So do I need a secondary equation? I do. Do I have, well, I'm going to have to. I got to have some more information. The rectangular page is to contain 24 square inches of print. What has to equal 24? There you go. I know that XY equals 24. So I can take that secondary equation, solve it for either X or Y, and substitute back into the primary equation. I'm just going to do y equals, what, 24 over x? So I've got my equation then. Area equals x plus 2 times y plus 3. I'm ready to start the optimization process, but I sure don't want to have to take a derivative where I'm going to have to do the product rule if I could do it easier. Let's go ahead and FOIL that out. Questions? In order to optimize, I have to take the derivative. What's the derivative of this thing? Keep going. Is that derivative ever undefined? When? When x equals 0. Is x equals 0 a viable option anyway? No. So the only viable options are positive x values, right? You getting x equal 4? What am I trying to do here? Minimize. I've got to prove to myself that that's a minimum. If x is 1, let's go right back here. If x is 1, is that derivative positive or negative? Negative. If x is 5, I'd have 48 over 25. Is 48 over 25 bigger than 3? No. So when x is 5, the derivative is, okay. I know that x equal 4 is a minimum. Questions? Now let's go see what we got to do with x equal 4. What should the dimensions of the page be? I know that x equals 4. How am I going to figure the dimensions of the page? Okay, so what's this? This is going to be 6 by x is 4, right? So what's y? 6. So 6 by 9. So we're going to say the dimensions of the page should be, what was the unit? I didn't look. Was it inches? The dimensions of the page should be 6 inches by 9 inches to use the least amount of paper. Hmm. Every time I've seen one of these done, it just says the dimensions are. I've never seen it where it says the width would be 6 and the height would be. I hear what you're saying though. Well, my first my first instinct is to say you're probably right. You probably ought to say the width of the page should be and the height of the page should be. True, true. The work does prove what side it's on. True. As I said, I've never seen it where it made you do that. It's always just said the dimensions would be. Okay, we've got two more to look at. A rectangle is bounded by the x and y axes and the graph of y equal 3 minus a half x. What length and width should the rectangle have so that its area is a maximum? So on this one, Chase, notice it says what length and width. So I will say the length should be and the width should be. Since it just asked for dimensions, it may just be the wording. So what length and width, what should the length and width be so that the area is a maximum? What am I trying to maximize? Area. All right. Well, I guess I better write an equation for area since that's what I want to maximize. Well, how do you find the area of a rectangle? Those are the variables that we've got, right? X and Y. Now, do I need a secondary equation? Because I have two variables. Okay, well, where's my secondary equation? What can I do? I've got it. That's my secondary equation right there. So we're going to do A equals X times. Again, I would certainly distribute. What's A prime? Oh, that's nice. 3 minus X. There's that X. That's where we substituted. So it's X times that Y value. All right, X equal 3. If X equal 1, is this derivative positive or negative? X equal 4. Does X equal 3 then maximize my area? Yep. So let's look at the question. What length and width should the rectangle have so that its area is a maximum? You know, let's do it this way. To maximize area, the length must be, we got X equal 3. Doesn't have any units on it, does it? No. Yep. I had it end at 0. Oh, why did I not have it end at 0? The reason here is that because X could be a negative number. Now you're thinking, well, I've got length and width, so I could have shut it off right there at 0. I sure could have. because we're talking about length. So I certainly could have done that. And what's the width? What is it? 3/2, because 3 minus half of 3. Yeah, since we're talking about length and I cannot have a negative length, I certainly could have closed it off at 0. Notice it wasn't an issue because I checked a positive number, but you're right. One more. Now, I guarantee you I'm going to do this one differently than the author does, because the author does it the hard way. And after we do this one, I would suggest that you look at what the author did. Okay. Determine the point on the line y equal 2x plus 3 so that the distance between the line and the point 1, 2 is at a minimum. How do I determine where's the shortest distance between me and that wall? Well, I can do a straight line that way. Perpendicular, yeah. So I know I'm looking for a point right in that region right there, yeah? What am I trying to minimize? The distance. Now, I'll just call it D. Remember how to find the distance between 2 points? The distance formula? Isn't there a song for that? And yeah, Cassie's back there. When finding the distance between 2 points. I don't know the rest of it. Okay. Those of you who are listening, some of them are singing the distance formula song, and Dylan is terrified. Now, all right, huh? How am I going to use Pythagorean theorem? Do you know it's one more? Huh? Do you know that? The point I'm looking for, this xy, is not necessarily at that y-intercept. Okay. We know that the distance between those 2 points is yeah, you better. Do I need a secondary equation? I have 2 variables. I have to have a secondary equation. There it is. Wherever I see a y, I'm going to substitute 2x plus 3. Two x plus 3 minus 2 is 2x plus 1. Now this is where the author and I decide to part ways. We diverge right here. The square root of 5 is bigger than the square root of 4 because 5 is bigger than 4. I am sure about that. The square root of 10 is bigger than the square root of 6 because 10 is bigger than 6, right? If I want to maximize this square root, then what I really want to maximize is the crap under the square root. I want to make the biggest number possible be under that square root. Would you agree to that? Oh, minimize. Then replace when I said maximize with minimize. Okay. So instead of taking the derivative of this, which I could absolutely do, I would have to do the chain rule because I'd have to put a big raised to the 1/2 power. That's what the author does. It's rather long, but very doable. But in order to minimize a square root, I need to, now I'm getting it right since I'm saying minimize, I need the smallest number possible under that square root sign, don't I? So I'm just going to minimize this. Aha. That's all I'm going to minimize. So let's call that something else. We can't call it D because we've got to change. That's not D anymore. Let's just call it Dylan wants to call it Jerry. That's why the J. Yes, yes, that is recorded for posterity. Was that you or was that just? Oh, that Zach wants to call it Jerry. So, all right. This is what I want to minimize right here. You can do chain rule on both of those, or you can FOIL them out, combine like terms. Which one do you think would be easier, quicker to do? I think just chain rule. I think it's going to be quicker. Try it. Try it. J prime. Come on, go. J prime. Times the derivative of the inside, which is 1. Done. If you want to FOIL those out and combine like terms, that is perfectly fine. Did I do that right? Plus 2. All right. Plus 2. That's J prime. Is that derivative either ever 0 or undefined? Correct. It is. It can be 0, never undefined. 0 when x is. If you do the chain rule and take the derivative of this bad boy right here, you're going to get negative 1/5 also. All right, let's check it. Wait, what? Is a negative number a reasonable? Can a negative number be an x value? Sure. So that's legitimate. There we go. If x is negative 1, is this derivative positive or negative? Don't say, oh, I need to minimize, so that's got to be a negative and that's got to be a positive. 0. X equal negative 1/5 does minimize our distance. Determine the point. Oh, we found x, didn't we? X is negative 1/5. What's y? Yep, 13/5. Minimizes the distance. To the point 1. I don't think optimization problems are hard. There's just a series of steps. Draw your picture. Write your primary equation. When do you write a secondary equation? When your primary equation has more than one variable in it. Get it in a position, in a shape where you can actually take the derivative. Find those critical numbers. Check them. And write a sentence.